Figure 1 shows a design for a bathing pool. The pool P, shown unshaded in the figure, is surrounded by a tiled area T, shown shaded. Tiled area is bound by the edge of the pool and by a circle C with radius 6. Okay, and then the center of the pool and the center of the circle are the same point. So here's our radius 6. And then we're told that the edge of the pool is modeled by the curve with this polar equation, 4 minus a sine 3 theta, where a is a positive constant, and we're then given that the shortest distance between the edge of the pool and the circle is 0.5, and asked to determine a. So the shortest distance is going to be here, and here, and here. There's actually threefold symmetry in this question. But it's going to be when r takes its largest value, and it's therefore going to be when 4 plus a, because I'm minus, remember, sine varies between -1 and 1. So if it's equal to 1, for example, we're going to get our smallest point, 4 minus a, our shortest distance from P, or the longest distance from the edge of the pool. If it's equal to -1, we'll get our biggest value of r, that corresponds with up here. And so 4 plus a is then going to equal, 4 plus a is going to equal 6 minus 0.5, because we're being told that that is 0.5. Or we could say that 4 plus a 0 plus 0.5 is 6. But either way, we're going to get a equal to 1.5. And for example, this is going to be when theta is pi over 2. Remember, this here is 0 angle. And then if you go all the way around to here, we get pi over 2. Then it'll be sine of 3 pi over 2, which is actually -1. That'll be one of them. And then, of course, we get some other ones as well. Hence, using algebraic integration, determine, according to the model, the exact area of T. So I can, first of all, work out the circle. That's going to be a good idea. Which is going to be pi times 6 squared, so 36 pi. And now to find out basically the non-shaded region. And this is how we're going to be doing it. We're going to imagine drawing a very small sector here. And if I wanted to find the area of that sector, I'm working in radians, it would be a half r squared times a really small angle that I've made, d theta. And then I just imagine, this is like you do when you integrate using our rectangular integration. So imagine then summing them up, and this is the formula to work out the area when we're dealing with in polar coordinates. Just trying to give you like a bit of motivation for where that comes from. So the non-shaded area, in our case, is going to be half times the integral from 0 to 2 pi, because I'm going all the way around. By the way, you could use threefold symmetry and do just 0 to 2 pi over 3 and then times it through by 3, but it's absolutely fine to do what we're doing here. Let's just keep it simple. And then it's going to be 4 minus 1.5 times sine 3 theta, or not sim, sine 3 theta. And remember, I'm squaring it. D theta. Okay, this is the integral that we need to find. So let's expand the bracket. We get 16 minus 6 sine 3 theta minus another 6, so minus 12 sine 3 theta. Then plus, well, that's 3 over 2, so plus 9 over 4 sine squared 3 theta. Good. Right, it's just that sine squared that's the trickiest. So, okay, you will have seen this before dealing with A-level maths and so on. Double angle formulae to deal with sine squared. And it's to use cos 2a. Well, it's cos squared a minus sine squared a. Actually, I will write that down. Cos squared a minus sine squared a. But we just want to get sine squared, so we replace cos squared by 1 minus sine squared. We get 1 minus 2 sine squared a. Rearrange, this means that sine squared a is going to be identical to a half minus a half cos 2a, which means this here, if I replace a by 3 theta, is going to equal a half minus a half cos 6 theta. Okay, we're ready to integrate. I'll keep the half outside, might as well. 16 theta, and I'm going to get 4 cos 3 theta. I'm doing reverse chain rule here, so I've divided through by 3, and sine integrates to minus cos, so it's going to become a plus here. You can always check back. If I differentiate it back, I times by the 3 to get the 12. Cos goes to minus sine. Sorry, I do the outside first, so cos of something becomes minus sine of the same thing, but then I times by the derivative of the inside. So yeah, it all checks out. Then I'm gonna, yeah, I've got the half. I mean, I could have collected some bit together. Remember, I'm timesing through by 9/4 as well, so it's going to become, oh yeah, I probably should have. It's just that bit that's a half minus a half cos 6 theta. So I'm going to get plus, it'd be 9/8 theta. And then I've got minus 9/8. Right, now just to integrate cos 6 theta, I'm going to be timesing by 1/6 and sine 6 theta. Okay, that's all good. Evaluated between 0 and 2 pi. Before I sub in 2 pi, I'm just going to combine the 9/8 theta and 16 theta. It actually becomes 137/8 theta. And now let's sub in. So I'm going to get a half. Remember, I have to show detailed reasoning, so I want to show enough working here. Sub in 2 pi, so 137/8 times 2 pi. Do this on your calculator, so we get 137/4 pi. Then we get 4 lots of cos 6 pi. This ends up being 4. When you put 2 pi into the sine 6 theta, it's a multiple of pi, so you're going to get 0 actually there. And then we're going to minus, well, 0 coming from here, but then we're going to actually be minusing 4 from here. So these cancel, and the sine again doesn't give us anything. So we're just left with 137/8 pi. And we're very nearly there. So remember, we want to find the exact area of t. So t is going to be that 36 pi we had for the circle minus 137/8 pi. Put that into your calculator and you get 151/8 pi. Nice question.